Okay, everybody, let's get started with the last chapter that we're going to cover this year, which is chapter 10. And up until this point, we have talked about a couple of different types of confidence intervals and tests. We have talked about a hypothesis test for the mean, where sigma is known, the mean where sigma is unknown. That was all in chapters 6 and 7 with confidence intervals and hypothesis tests. Plus there we talked about confidence intervals, and we didn't do the hypothesis test for a proportion. Then when we got into module 5, chapter 9 was about linear regression, and there was a hypothesis test with that. And then chapter 10 deals with something called chi-squared tests. So I'm going to kind of go through information on sections 10.1 and 10.2. I would also strongly encourage you to watch the video instruction in the multimedia library of MyStatLab. Their video instructions are really good, and they can also help you understand some of the things that I'm going to say as well. So the first type of chi-squared test that we are going to do, and chi-squared is, if you know anything about the Greek alphabet, it kind of looks like a squiggly X. That is chi-squared. So that's what we're talking about. Not chi, it's chi. So the first one we're going to talk about is called the goodness of fit. And the goodness of fit test has multiple categories. But only one variable. So maybe we're talking about M&Ms and the different colors of M&Ms, and there may be 6 different colors. So the variable would be color, but there's 6 different categories of color. The idea behind a goodness of fit test is that the null hypothesis is that all proportions are as expected, and the alternative is that not all proportions are as expected. So, for example, the M&M example that I said, the Mars Company says that there are specific percentages of each color in a sample of M&Ms. Well, you get a bag of M&Ms, you open them up, you count them, you calculate the proportions of each color, and you see if they're what Mars says they should be. That would be an example of a goodness of fit test. So that's the null and alternative, and we would need to have these in context. So if I was doing the M&M problem, I would say all proportion of the colors of M&Ms are as expected. The formula is not existent. We're not going to do this for actual confidence intervals. We're only doing hypothesis tests. So we need to look at the next thing, which is assumptions. We do not have normality, because what happens, and let me show you the chi-squared chart, and this document will be added to your resources. But the chi-squared table is always positive. That's why you have an x and y axis. And it's not necessarily normally distributed. And what we're going to do is always going to be a one-tail test. We're not going to do two-tail. So our assumptions are still that we have a simple random sample. And then this time, all expected values must be greater than or equal to 5, for it to be appropriate to use a chi-squared test. And like I did with the mean, it was greater than or equal to 30. With proportions, it was n times p and n times q had to be greater than or equal to 10, and now we're greater than or equal to 5. So just be careful with that. You're not going to have to list these, but you will see this addressed whenever you watch the videos in my stat lab. So when we talk about the rejection region, your rejection region, like I said, is going to be all positive. We're only going to use one tail. That tail does consist of all of the alpha level. And for this test, to get the critical value, the chi-squared critical value, you're going to use degrees of freedom equal to k minus 1, where k is the number of different categories. Now to calculate the test statistic, because all of your calculators will not do this, this is the only one that the calculator won't necessarily do, but it's not hard to do by itself. So you can create a chart, because the test statistic formula is to take the sum of all the observed values, so that's what actually happened, the observed number, not percentage, but the observed number, minus the expected number squared divided by the number of expected. So you'll see it written as the sum of O minus E squared over E. So you'll create a table. You will have the expected percentage. Then you'll have the observed. Then you'll have the expected number. And the way you get the expected number you take the total in the sample, so that's n, times the expected percentage. And then you're going to do observed minus expected. And then we're going to make one more column of observed minus expected squared. So you'll square each of those numbers. And then you're going to sum that, observed minus expected squared, and divide it by, excuse me. Nope. You're going to take each of those, divide it by the expected, and add them all together. So once you have done your rejection region and you add up that observed minus expected squared divided by expected, if it's greater than the critical value you found, you reject. If it's not, you fail to reject. So let's look at a problem. And here's the information that I was just going over as far as observed and expected and all that kind of stuff. So let's look at an example. A tax prep company randomly selects 300 adults, so that's your N, and asks them how they prepare their taxes. The results are shown below. Perform a chi-square goodness of fit test to test whether the distributions are different. So we are going to do the observed would be these numbers: 71, 40, 101, 35, and 53, and that should equal 300. Now I'm going to open my calculator real quick and show you how it's easy to do this in the calculator. Come on. Always gotta love it. There we go. Okay. So I'm going to go to Stat Edit, and I'm going to put my observeds in list 1. So 71, 40, 101, 35, 53, and then I'm going to do my percentages times 300 to get my expected. So this is 300 times 0.25, which is 75. Then 300 times 0.2, which is 60. 300 times 0.35 is 105. 300 times 0.05, make sure you do 0.05 and not 5, which is 15. And then 300 times 0.15, which is 45. And if you add those up, you should get 300 as well. So some are higher, some are lower. Some are off a little bit, some are off a lot. But now we're going to do observed minus expected. And then we're going to do observed minus expected squared. So 2 more columns. But I'm going to have the calculator do that for me. So I'm going to go up to list 3. And I'm going to do list 1, second one, minus list 2. So I get -4, -20, -4, 20, and 8. So now I'm going to take each of those numbers and square it. And I can just take L3 squared. Whoops. So I need to clear this and put L3 in parentheses and square. Nope, that was to the -1. Square. There we go. So squared is 16. I know it's hard to see that. 416, 464. 16, 4, which you could have done on your own. 16, 464. So I'll come back to this in a second. My null is that whether the distributions are different. So the proportion of tax prep of how people prepare their taxes is the same. The proportions of how people prepare their taxes is the same. Or your alternative, the proportions of tax prep differ. My level of significance is 0.01. I'm going to go to my chi-squared table, and I have 1, 2, 3, 4. So my degrees of freedom is going to be 4 minus 1, which is 3. And my critical value is chi-squared greater than so degrees of freedom is 3, and my alpha level is 0.01, so 11.345. 11.345. So if I get a test statistic that's greater than 11.345, then I am going to reject. So don't worry about this p-value, because unless you've got the thing to do on the calculator, that'll do it on the calculator. Well, actually, no, we can do p-value. I'll show you how to do it. All right. So for the test statistic, I'm going to go back to my calculator. I am going to take list 4, because that was observed minus expected squared. And I'm going to divide it by list 2, which was my expected. So what I just did was had the calculator do the observed minus expected squared and then divide it by expected. And then I need to add all that up. So to add, you're going to do second, stat, math, 5, and that was an L5. So 35.1213. So chi-squared equals 35.12. So I did, you can do these individually. You could take 16 divided by 75 plus 400 divided by 60 plus 16 divided by 105 plus 400 divided by 15 plus 64 divided by 45 and gotten that. For the p-value, you're going to go to chi-squared CDF. You're going to put in the test statistic, comma, degrees of freedom. Chi-squared CDF is where all the CDF stuff was, which is second vars. If you scroll down, you see chi-squared CDF. The lower, the lower is 35.12. The upper is second e to the 99th, because you're going to go to infinity. Degrees of freedom is 3. So let me erase that. So this is the test statistic to infinity, and then degrees of freedom. And if you hit enter, it gives you something e to the -7th, which means move the decimal left 6 places. So that is approximately 0. That's smaller than 0.01. 35 is bigger than 11.345, so we reject. And our conclusion is there is enough statistical evidence to reject the null and conclude there is a difference in the distributions. So that is the chi-squared test for goodness of fit, which is on section 1, 10.1. Now, if you're lucky enough to have a new enough calculator, when you go to stat and go over to tests, you might have a chi-squared GOF test. This one, the chi-squared test, that doesn't do it. It's the chi-squared GOF test. And if you're lucky enough to have that, you put your observed in list 1, your expected in list 2, you have to tell it how many degrees of freedom and hit calculate. And there is your test statistic, and there's your p-value. And there's all of your observed minus expected squares. But if not, you can still do it by hand. It just takes a little longer. So that is section 10.1. Section 10.2 is the chi-squared test for independence. Or homogeneity. Same setup, looks the exact same, the only difference in how the question is asked. For homogeneity, it will say, is there a difference in one variable relative to another? Independence will say, are the two variables independent, or is there an association between the variables? So, two different names for the test. They work the same, they look the same. The only thing that's different is how the question's asked, which makes it a little bit different on how you write the null and alternative hypothesis. This will be given to you in a two-way frequency table. It'll have a variable across the top and a variable down the sides, and it will have multiple rows and columns, whereas goodness of fit only has one variable. So looking at the null and alternative for homogeneity, the null is that there is no difference in one variable relative to another. And the alternative would be there is a difference. in one variable relative to another. And then for independence, the null is that there is no association between the variables. And if there's no association, they're independent. One doesn't affect the other. That's what you assume is true unless you prove otherwise, and therefore the alternative is that there is a relationship or an association between the variables. Or they are dependent. For the chi-squared critical value, degrees of freedom equals the number of rows minus 1 times the number of columns minus 1. And that'll be the degrees of freedom you look up in the chart with a given significance level. For the calculator, this test, regardless of how old your calculator is, this test will be in the calculator. It's the chi-squared test, not the one that says GOF. But you have to put your observed in matrix A. And I'll show you where on the calculator you go to do that. So let's look at an example. So here is our two-way contingency table. We have two variables, favorite way to eat ice cream and gender. And so when we talk about the null and alternative, it says, can you conclude adults' favorite ways to eat ice cream are related to gender? So that would be relationship, association, independence. So you would say for the null, there is no relationship between gender and the way adults eat ice cream. And I apologize for my handwriting because on this slate it's very ugly. So no relationship for the null. The alternative, there is a relationship. The way homogeneity would look is if it says something like, is there a difference between men and women? Or do men have different ways to eat ice cream than women do? Then that would be homogeneity, but it's still run the same. You just write the null and alternative differently. There is a relationship between gender and the way adults eat ice cream. It tells you to use an alpha level of 0.01. The critical value, if you look back at the problem, there are 2 rows and 1, 2, 3, 4, 5 columns. So for the critical value, we're going to do 2 minus 1 times 4 minus 1. That's 1 times 3, which is 3. And we already know that one to be chi-squared critical value greater than Sorry about that. 11.345. So to show you where to go to matrix on the calculator, you're going to go to second x to the negative 1, which is where matrix is. You are going to edit matrix A, which is a 2 by 4 matrix. Then we're going to put our numbers from our table, just the numbers, into our calculator. So 600, it's going to go across, 288, 204, and I did that wrong because it's got 5 rows, 1, 2, 3, and so I need to change my degrees of freedom also. I'll go back and do that in a second. So 600, 288, 204, 24, 84. And then the second row, 410, 340, 180, 20, and 50. And so once you have it in there, all you do is go to Stat, go over to Tests, go down to chi-squared test, hit enter, and enter. There's your test statistic, 32.6266. .6266. P-value is approximately 0. That's smaller than 0.01. And let me go back to my table here. And so I should have done 5 minus 1 instead of 4 minus 1. So instead of 3 degrees of freedom, it's 4. So it's 13.277. Let me change all that. So this should have been 5 minus 1. This should have been 4. And this should have been 13.277. Since 32 is greater than 13.277, we can reject. And you say there is enough statistical evidence, or enough evidence to reject the null. And conclude there is a relationship between gender and the way adults eat ice cream. And there you go. The homework is up, the lab is up, and we will have a Zoom meeting next Tuesday before I open up your test. Good luck, guys.